Hello guys and welcome back to my channel Civil Construction and Tutor, and in this video we'll discuss about design of an combined footing. So we have a question here. Design and combined footing with a column A of dimension 300 by 300 mm and column B 400 by 400 mm carrying load 300 kN and 400 kN respectively. Make sure these are the unfactored, or we can say service load. Column A is near to the edge, that this edge means the property line, and the distance of column A is, or the distance of column A face is restricted to 0.42 meter from the property line. If we assume this is the property line, then the distance of this face of the column A is 0.42 meter. The soil bearing capacity is 150 kN per meter square. Take M20 concrete and Fe 500 steel. The center to center spacing of the columns is 2.5 meters. So this is a column and this is another column. So the distance between these two columns is 2.5 meter. So these are the given data. So let's start with the solution. And the given terms are PA, that is the load on column A. This is 300 kilonewton, and the design load will be 1.5 times of the service load. So this is 450 kilonewton. Similarly, PB 400 kilonewton, and this is 600 kilonewton. So make sure here we have lighter column, that is A, towards the edge, and the column with the heavier load on the central side, or we can say to the other side. So on the property edge we have a lighter column. Generally, if we see, the column near the center of the building or the structure are subjected to heavier load as compared to the column at the edges. For column A, so these are the dimension. We'll consider the longer side as the width and the shorter side of the column as the depth. For now we have equal dimensions, so it is not a thing to worry about. So BA is, so width of the column A 0.3 meter. Similarly, depth is 0.3 meter, and for column B it is 0.4 and 0.4 meter respectively. Soil bearing capacity is 150 kN per meter square. Characteristic strength of the concrete is 20 Newton per mm square. Yield strength of the steel Fe 500, so 500 Newton per mm square. Center to center spacing of the column is 2.5 meter, and the projection of column A face from the face to the property line is 0.42 meter. In some cases we might have column being flush to the property line, so there will be zero projection. That will be a different case. So for now we have 0.42 meter. So if we see in the figure, then the column A is 0.3 by 0.3. Similarly, column B is 0.4 by 0.4. The center to center spacing between them is 2.5 meter, and the distance of the column A from the property line is 0.42 meter. The very first step we have is to determine the length and the projection for the footing. So first step, proportioning of length and the projection, and to that we'll find area required for footing as we did for the isolated footing. So area required for footing is equal to total load by soil bearing capacity, and for this case we'll assume 15% as the self weight of footing, or you may also consider 10% as the self weight of footing. But for keeping it safe for the gross bearing capacity, I am assuming 15%. So 1.15 times the service load, 1.15 PA plus PB, and this comes as 805 divided by 150. So the area required is 5.4 meters square. And there is a different way for considering the length of the footing, which is different than that of the isolated footing. So in the combined footing, we may have equal loads for the column, or we may have unequal loads of the column. For unequal loads, projection near the lighter column, so this is the lighter column A, and the projection must be fixed. But in our question we are already been provided with the projection, so we don't have to fix. But if it was the case where we are not provided with the projection from the property line, then we had to fix it first and then determine the length of the footing. So that is the one point we have to understand. And similarly, the center or the CG of the footing must coincide with the center of gravity of the column loads. So that means these are the two loads acting, and this may be a center of gravity of the footing. So these must lie on the same plane. So this is the concept we have to understand. So let x bar be the distance of center of gravity of load from the center of the column A. So if we see this in free body diagram, okay, so this is the center of the column A, this is the center of the column B, and we assume that the center of the gravity of the footing is at distance x bar from the center line of the column, and making sure that the all this that is the resultant of the load and center of gravity of the footing lies at the same point. So for which we'll use this concept, that is, we'll consider this point and take value with respect to center of gravity. So PA into x bar must be equal to PV into 2.5 minus x bar, considering this as the center point or the center of gravity. Okay, 300 and this is 400. So we get x bar is equal to 1.43 meter from the center of the column A. So we'll get the center of gravity, or we can use this concept to find the center of gravity of we can say CG x bar resultant. So summation pi by xi summation pi. So PA into x1 plus PV into x2 PA plus PV. So we are considering the point to be taken from the center of column A, so for which the distance will be 0, x1 will be 0, x2 will be 2.5, and PA plus PV you can substitute the value, then we'll get 1.43. so this is the same, but you can do either way. So I'm again making you clear, for columns with varying load, the projection from the lighter column has to be fixed, then the length of the footing has to be computed. But as the question has already fixed the projection, so we don't have to worry about it, and it is 0.42 meters. So x is equal to 0.42 meter, and to determine the length of the footing we have to understand the concept about center of gravity. So if we are assuming this as the center of gravity, then this portion and okay, this much portion and this much portion should be equal. That is the concept of center of gravity. Then using that concept, XA, so XA basically it is the length from the left edge of the footing to the center line of column A. So XA plus X bar up to center of gravity should be equal to L minus X bar, means this much portion, plus projection from the center of column B to the right edge of the footing. Okay, so XA plus X bar is equal to L minus X bar, which is this much portion, plus 1.43. okay, that is XB, sorry. So XB we are trying to find it. Now here we have XB is equal to XA. So XA basically means X plus this much, that is half of the column width. So X 0.42, width of column is 0.3 divided by 2, so it comes as XA plus X bar is 1.43, which we computed recently as the center of gravity distance from the center of the column A, and then we have L, which is 2.5 minus 1.43, we get 1.07. so finally XB is equal to 0.93. then the length of footing will be XA plus L plus XB. okay, so that comes as 4 meter by substituting XA as 0.42 plus 0.3 by 2 plus 2.5 plus 0.93. or you can do, as I said, this much distance should be equal to this distance. Then we have XA and XA and X bar will be this much distance, so 2 times of XA plus X bar will give the length of the footing, which will be 4 meters. So I just tried to make you clear about this concept, or you can directly use this also. So we have computed the length of the footing. Now width of the footing, BF, so area required by LF will give the footing dimension or footing width. So 5.4, which we have computed, and LF, which is the length of footing, 4. Now this comes as 1.3 meter. The width of the footing should not be generally kept equal to 1.5 or greater than 1.5. okay, considering the municipal rule. So we'll provide 1.5 meter as the width of the footing, and length of footing as 4 meter. So finally area provided is 6 meter square. The required area was 5.4 meter square and the area provided is 6 meter square, which is safe. So if we see in figure, the length of the footing is 4 meter, width of the footing is 1.5 meter, the center or the distance or projection from the left edge to the center line of column is 0.57, to the face of the column it is 0.42 meter. 0.3, 0.3, the center of gravity lies at a distance 1.43 meter from the center of the column A. Similarly, the projection from column B to the right edge of the footing is 0.93 meter. Now here you can see we have to find the net upward swell pressure. We consider this point, that is also the center of gravity of the footing must coincide with the resultant of the column load to ensure that the pressure distribution under the base of the footing is uniform. So to make sure this as a uniformly distributed load, we have to consider the swell, the center of gravity of the footing coincides with the center of gravity of the load. And for net upward swell pressure, we have summation sigma is equal to PD by area provided. We don't have any moment for now, so design load divided by area provided, 1.5 times of 300 plus 400 divided by 6, as the area provided is 6 meter square. So this comes as 175.1 kilonewton per meter square. Now swell pressure per unit width, this is for the area, but we will design the footing separately, that is for the longitudinal direction as well as the transverse direction. So we have to consider swell pressure per unit width, that is along the longitudinal direction. So for which sigma into BF, that is width of the footing, 175.1 into 1.5, with the footing is 1.5, so this comes as 262.7 kilonewton per meter. I hope you can get. Now you can see this is the simple diagram of the footing and it is subjected to UDL of 262.7 kilonewton per meter. The design load on the under the column A is 450, similarly under B it is 600 kilonewton. Now the hard step is to calculate longitudinal bending moment and shear force. And for shear force, if we see this is the point A and this is the point B, we can say this is a continuous beam with two overhang portions. So for which the bending the shear force diagram will be something like this, and the value is computed as, if we see shear force at C, okay, at left of C and right of C, it will be 0 because there is no any support or there is no any reaction provided on support C. So if there is no any reaction or support, there won't be shear force at that particular point. So shear force at left of C and left of right of C is equal to 0, and we are going from left to right, and for which the clockwise or the upward force will be positive and the downward force will be negative. Similarly, shear force at the left of A, as I said, we are going to from left to right, for which the upward force will be positive and the downward force will be negative. So shear force at left of A, so we are considering the left side, and for the left side we have a UDL being acting, and for which it will be 262.7 into the span, and the span is 0.57, that is the cantilever projection from the center of the column A. So this comes as 150 kilonewton positive, because as I said we are going from left to right, and for left to right the upward force will be positive and it is upward force, so 150 kilonewton. Shear force just right of A, at just right of A there is a axial load acting downward, so 150, that is at the left of A, minus 450. Why? From left to right downward force will be negative, so minus 450, and this comes as minus 300 kilonewton. Similarly, considering point B, now let us come from right to left. As I said, from right to left upward force will be negative, downward force will be positive, and shear force at right of B, okay, right of B, 262.7 into 0.93, okay, as I said, from right to left, upward force will be negative. So 262.7 into 0.93, that is the projection length. At the right of B we have UDL only, so minus 244 kilonewton. Shear force at left of B, minus 244, that is at just right of B, plus load from column B, which is 600, from right to left, downward force positive, so plus 600. This comes as 357 kilonewton. I hope you are getting this point. Similarly, shear force at D, as it doesn't have any support or reaction, so it will be 0 on both left and right. Now let us draw the shear force diagram. So at this point we have 0, that is at C, and at left of A we have 150 kilonewton, which is positive, and at right of A we have minus 300, so downward, and at right of B, or we can say at left of B, first we will calculate left of B, we have 357, which is positive value. So there is a change from negative to positive. That means there is a point where there will be 0 shear. Similarly, at right of B we have minus 244, which will be a negative, and then again at point D we have 0. So this is the shear force diagram. Make sure to understand that there is a point of 0 shear. Now let us calculate the distance. So for calculating the point of 0 shear from the center of column A, we will use a similar triangle property. So this was the shear force diagram. I have just written these two values because we are interested with these two triangles. If we consider at a x distance from the center of column A, then 300, or we can say we will start from this, like 2.5 minus x divided by 357. So basically this divided by this is equal to x divided by 300. Now on solving this, we'll get x is equal to 1.14 meter. Similarly, point of 0 shear. So this is from the center line of column A. Don't get confused. Now point of 0 shear from the right edge, that is from this point, what it will be? This projection plus 2.5 minus x, then we'll get this distance, so which is 2.29 meter. Similarly, point of 0 shear from the left edge, this projection 0.57 plus x, we will get 1.71 meter. At point of 0 shear, maximum bending moment occurs. So we are calculating maximum bending moment, and then we will calculate reinforcement according to the maximum bending moment. So bending moment is equal to, here you can see this is the point of 0 shear at a distance 1.14 meter from the center of the column A. Then for calculating bending moment at this point, we have 262.7, this is the UDL, 262.7 into this distance plus this, which is 1.14 plus 0.57, basically 1.71 meter. Okay, the span of the UDL up to this point is 1.71 meter. Square divided by 2, because for UDL bending moment will be W L square by 2. So that is W into L by 2, minus, because we have a downward load acting at point A, so 450 into 1.14. Now this comes as minus 128.9 kilonewton meter. So this is the maximum bending moment which occurs at the point of 0 shear. Similarly, you can calculate from the right side also. It should come equal to the value computed from the left side, because we have calculated it considering that the center of gravity of the footing and center of gravity of the load will coincide, and due to which the pressure distribution will be equal, hence we will get equal bending moment from either side. So that is why fixing the length of the footing has to be considered properly to ensure that the moment comes equal from either side. So 262.7, which is the UDL, into this much length, and I have just computed this as 2.29 meter. So if we add these all terms, you will get 2.29 meter, square by 2, WL square by 2, minus 600, because this is the downward load, into 2.5 minus 1.4. so we are considering this much distance, and the sign convention will be same, that is left to right. Here you can see left to right clockwise positive, anti-clockwise negative. So if we see from left to right, then 262, this gives a clockwise moment to this point. Similarly 450 gives a anti-clockwise moment, so it is taken as negative. And considering this part, right to left, anti-clockwise positive. So if we see, this will give anti-clockwise, that is the UDL gives anti-clockwise moment about this point, and this gives a clockwise point, so this will be negative. And both values will come as 128.9. so I forgot here 128.9, so this also comes as 128.9. So now let's calculate bending moment along the projection. We computed at a point 0 shear where the maximum bending moment occurs. Now let us see bending moment along this projection. So we'll understand the bending profile of the footing. So bending moment under column A, bending moment is equal to, this is UDL. So for UDL, as I have already said, it will be WL square by 2. The length of the projection is 0.57 and this is 0.262.7 kilonewton per meter. So you can understand this, the column face being as a fixed end, and this much portion will be acting as a cantilever beam, and for this we'll calculate a bending moment as W into L into resultant, or we can say centroid of the UDL, that is L by 2 for the UDL. So 262.7 into 0.57 square by 2, this comes as 42.7 kilonewton meter. Make sure to understand this point. We are considering this point from left to right clockwise positive. So this is giving clockwise moment considering point A. So this is plus, that is sagging. Similarly for bending moment under column B, if we see WL square by 2, W being 262.7 into 0.93 square divided by 2, and from right to left anti-clockwise positive. So 262.7 into 0.93 square by 2, this comes as 112.9, which is also positive. But while we calculated the maximum bending moment, we found the value to be negative, okay, minus 128.9. so that means there is a change in the bending profile, that is on the projections the bending moment or the bending profile is sagging, while at the mid span it is hogging. So if we see that, we found that the bending profile of the footing is something like this. This much portion acts as a cantilever, and due to the action of the swell pressure, it bends upward, giving a sagging moment. Similarly, this also gives a sagging moment, and at this portion we have a fixed end on both ends, it gives a hogging profile. So I hope you are clear about the shear force diagram. We have already done this. At 1.14 meter from the center of column A, the value will be 0, and according to that the maximum bending moment occurs at the point 0 shear, and the maximum bending moment was 128.9, which was a hogging moment. And at the support we found the value, the sagging moment was 42.7 at this projection, and for this projection we found this as 112.9 kilonewton meter. So if you see, you can understand from this point also, this portion, that is the mid span, suffers hogging moment, and the reinforcement has to be designed as per this, that is the hogging moment. And similarly for the support projection, if you see, we have to design as per the sagging moment. This portion undergoes tension, so we will provide reinforcement, negative reinforcement as per the hogging moment along the longitudinal direction. Next step is to calculate the depth of the footing. Either you can go from the bending consideration or you can use one-way shear consideration. The basic difference will be that from bending consideration you will get higher percentage of steel and smaller depth, and from one-way shear consideration you will get lesser steel but higher depth. So from bending consideration I'll show you both, because some of you may follow bending consideration and some of you may follow one-way shear consideration. So the maximum bending moment was minus 128.9 kilonewton meter. Don't go with the sign, we are interested with the value only, with the magnitude. And for FE500 from SP16 we have mx by fck bd square. So this is from the table C, I guess. Mx by fck bd square is equal to 0.133 on cross multiply, d square is equal to 128.9 into 10 to the power 6, converting this into Newton mm, divided by 20 fck into 1.5, this is width into 1000, converting this into mm. Finally we get d is equal to 180 mm, and for shear consideration it is taken as 2 to 3 times greater the value that we have computed from the bending consideration, and we provide overall depth as 550. So basically this is the effective depth, and considering overall depth will provide 550 mm, and substituting the or subtracting the effective cover and bar size, we get this 492 mm. So how this value comes, I'll talk in this part. Okay, the another way is from the one-way shear consideration. In this part, as I said, we will have less steel but we will have higher depth, and that is due to we will assume a value for the percentage of steel in the pre-calculation, so percentage of the steel can be controlled in the analysis part. Then page number 175 of SP16, we can compute the design shear strength tau c with respect to p% and grade of concrete. If we see in the code, you can find tau c is equal to 0.85 under root 0.85 into fck into 1 under root 1 plus 5 beta minus 1, this is outside the bracket, divided by 6 beta, where beta is equal to 0.8 fck by 6.89 into percentage of steel. 0.8 into 20, considering fck as 20, 6.89 into 0.15, because we have considered percentage of steel as 0.15. This comes as 15.48, and the value of beta should not be less than 1. If it is less than 1, take value of beta as 1. Then tau c we can compute, substitute the value 0.85 under root 0.85 into 20, 1 plus 5 into 15.48, this is in the whole bracket up to this term, minus 1, this is minus 1 not plus 1. Okay, divided by 6 into 15.48, we get 0.28 Newton per mm square. You can also compute design shear strength from the table 19 of IS 456 by linear interpolation. So from which we will get tau c is equal to 0.28 Newton per mm square. So this is from the linear interpolation, and this is from the direct formula. Now we'll use a relation to calculate the depth of the footing. We know shear strength of concrete should be greater or equal to shear stress, or we can say shear force acting on the footing. This is from the one-way shear consideration, and for one-way shear consideration, the critical section lies at a distance d from the face of the column. So as I said, it is critical at the section d distance from the face of the column. In general, the footing is not provided with the shear reinforcement, as it is an expensive way of construction, as the footing should be dependent on the depth rather than the shear reinforcement. Now shear strength of concrete is nothing but tau c into b into d. So this is the design shear strength into b into d. So this is Newton per mm square into this comes in mm square. So we will get in Newton, that is the strength, should be equal to or greater than that of the Vmax, maximum shear force, minus d plus b by 2 into sigma m. Why this is? Because the maximum shear force is 357, which we found for the column B. So we will determine on the basis of the maximum shear and at a distance d. So the 357 value was for the at the left of the column B. So we will consider from this face at a distance d. So at a distance d, we will consider the maximum shear force. Okay, Vmax, that is 357 minus d plus b by 2 into 262.69. It is nothing but we are considering the UDL. Okay, at a distance d, if we suppose this point, and the value 357 was considered at the center of the column, so we are also assuming this span while calculating the shear force due to the UDL. So d plus 0.4 by 2, because the width of the footing is 0.4. So 357 minus d plus 0.4 by 2 into 262.69, it is nothing but the UDL. On solving, we get d as 445 mm, but from bending consideration we got d as 180 mm only. So it is not safe, hence we have to take 2 to 3 times greater the value of the d computed. So on solving, we got this. Taking the maximum values, will provide overall depth as d is equal to 550 mm, clear cover 50 mm, and assuming the bar size in the longitudinal direction as 16 mm, we'll get effective depth as 550 minus 50 minus 16 by 2. Why? So if we see this as a reinforcement placement of the footing and we are considering the longitudinal direction, and the reinforcement provided for the longitudinal moment will be this. Clear cover is 50 mm and the effective depth is taken up to the center of the main reinforcement. So as we said, we are providing 16 mm longitudinal bar, so 550 minus 50, that is the clear cover, minus 16 by 2. So this comes as 492 mm. Now let us compute gross bearing capacity. So as I said, we have to keep a greater value to ensure gross bearing capacity, and I took 15% to compute a greater area required, and then it will be safe for the total bearing load. So the total load acting on the footing is pressure due to the axial load from column plus self weight of the footing plus weight of the backfill, and the pressure due to axial load is nothing but 300 plus 400 by 6. This is load divided by area provided. Okay, self weight of the footing, so this is the footing and the depth is 550 by 1000, converting depth into meter into 25 unit weight of concrete, so it is 25 kilonewton per meter cube plus backfill. Generally the depth of footing is provided as 5 feet and this comes as 1.52 meter minus 0.55, so this is the depth. I am subtracting the depth of foundation because the backfill will be this much only, so 1.52 minus depth into 18 unit weight of soil, 18 kilonewton per meter cube. So this comes as 148 kilonewton per meter square, which is less than the bearing capacity of soil, so it is safe. So hence the area provided is safe from bearing failure. Now let us calculate the area of steel and rebar sizes. So we have longitudinal reinforcement as well as transverse reinforcement in combined footing. So for longitudinal reinforcement at top, it will be different for top as well as bottom, because as I have said, the top reinforcement is provided for the hogging moment, while the longitudinal reinforcement at bottom is provided for the sagging moment. So for longitudinal reinforcement at top, we consider hogging moment, and bending moment or the maximum bending moment is 128 kilonewton meter, and from IS 456 2000 Annex G we have a formula to compute the area of steel required. Basically the formula is in terms of moment, that is moment is equal to 0.8 Fy AST, something like this. I have just modified this value to this, so we'll get AST is equal to 0.5 FCK by Fy into 1 under root 1 minus 4.6 mx divided by FCK BD square into BD. Substitute the value 2500. Maximum bending moment is 128 into 10 to the power 6, 20 into width of the footing is 1500, converting this into mm, and the effective depth is 492 square, 1500 into 492, so the value comes as 616 mm square. So this is a small value, so we have to check with the minimum steel. Minimum area of steel is 0.12% of BD, 0.12 by 100 into 1500 into 550. So the minimum area of steel is 990 mm square. But if we are doing with respect to one-way shear consideration, then we have to make sure that we are taking this value, that is 0.15%, because we computed the depth considering 0.15% steel. So 0.15% of BD, this comes as 1237.5 mm square. Assuming 516 mm as we have already done while calculating the effective depth. So that was the pre-assumption. Now we are assuming this value in the final stage. So spacing required will be width of footing divided by area of steel required divided by area of individual rebar. So 1500 1237.5 divided by pi into d square by 4. So d is 16, so pi into 16 square by 4. So this comes as 243 mm. So for spacing, now you can see here in table number 15 of IS 456 page 46, the clear distance between bars, that is the spacing, for FE 500 it should be 150 mm or it should be smaller than 150 mm, and hence even though the value calculated is 243, we will provide 150 mm center to center spacing. Then the number of rebars required. So here you see we are providing this longitudinal reinforcement along this direction, that is BF, and we have to provide spacing on both sides. Hence the number of rebars required 1 plus, because from this value we will get the number of spacer, and we have to add 1 to get the number of rebars required. So now 1500 is the width, minus 2 into 50, because 50 is the clear cover, divided by 150, then we will get 10 numbers of bar. Hence provide 10 number of reinforcement of 16 mm bar at 150 mm center to center as longitudinal reinforcement at top. Okay, so in this direction at top we will provide 10 number of rebars at 150 mm center to center spacing, and then the area of steel provided will be 10 into area of rebar pi d square by 4, so this comes as 2010 mm square. Similarly, longitudinal reinforcement at bottom, that is for sagging. The bending profile, that is at the midpoint or at this portion there is a tension, or this is the tension region, hence we provided the reinforcement at top considering this moment. But for the other section, that is for this bottom portion, we have to provide as per the sagging moment, that is considering the point of this is the projection. So we'll provide longitudinal reinforcement at bottom for the sagging moment. So maximum bending moment for sagging was, bending moment max is equal to 112.9 kilonewton meter under column B, which we have calculated previously. So if you see in the bending moment diagram also, this was the sagging moment. Similarly, as per 456/2000, using this formula we can calculate the area of steel required. Substitute the value M max as 112.9, B will be 1.5, D will be 492, and we'll get 538 mm square, which is considerably smaller value, but considering one way shear provides 0.15% steel. So if you are, or if the depth is calculated considering one way shear, then we have to provide the steel that we had assumed. But if we have designed by considering the bending moment, then we have to provide minimum steel, that is 0.12% of BD, which you can find in the code. So here you can see minimum reinforcement. For mild steel it is 0.15% of the total cross sectional area, but generally we use high yield strength deformed bars, so we'll use 0.12% if we are using the bending moment consideration. So for now I am using one way shear consideration, so we'll provide 0.15% steel. So area of steel required, minimum steel, is 0.15% of BD. So substituting B as 1500 and D as 550, we get 1237.5 mm square. So provide 10 number of 16 mm bar at 150 mm center to center as longitudinal reinforcement at bottom. Area of steel provided will be 2010 mm square as well. So as there is sagging and hogging moment, so there exists a point of contraflexure. So if you see, it is not the exact profile of the bending moment, just I am saying that for a UDL it will be a curve type, so I'm just representing it in the terms of, in the form of curve. So as we see, there is a point of contraflexure, that is the point at which the bending moment changes its sign. So point of contraflexure from center of column A, so we have to determine this distance, assuming this distance as x from the center line of the column A. Now we have summation MC, so C being the point of contraflexure, so let us write PC. Okay, so this is PC. Summation of moment or moment about this point should be equal to 0, and for this we consider this much portion, that means this much portion. So we have UDL and a point load being acting here. So we are considering from the center of column A and from left to right clockwise positive. So 262.7, this is the bending UDL into x plus 0.57. so this distance being x from the center line of column, and this being the projection, 0.57 square by 2 minus 450 into x is equal to 0. So this will come in terms of quadratic nature, you can solve, and then on solving we'll get the value of x as 0.15 meter and 2.13 meter. X is equal to 0.15 meter. Similarly, x is equal to 2.13 meter up to this point. Now shear force at the point of contraflexure. So we'll compute this value. So this may be necessary while computing the curtailment of the longitudinal reinforcement at top. Okay, so this is the shear force diagram, and we are trying to find the shear force at the point of contraflexure. So this is the point of contraflexure which occurs at a distance 0.15 meter. So you can use the similar triangle rule to find this value. This is the value which we are interested to find. So here shear force is equal to minus 300, that is nothing but this value, plus 262.7, that is the UDL, into 0.15 meter, that is the span of the point up to the point of contraflexure from the center line. So this comes as minus 260.7. You can also use a similar triangle. 300 by 1.14 is equal to x divided by 1.14 minus 0.15. You will get the value. Similarly, shear force 2, that is at this point. Okay, this will be a positive value, you can see, and it is nothing but 357. This is the maximum shear value, 357 minus 262.7, that is the UDL, into 2.5 minus 2.13. So as we have computed 2.13, so we are interested with this value. 2.5 is the center to center distance between column, minus this distance, we will get this value. So we can compute, and this value comes as 260.31 kilonewton. So these two value will be necessary to check for the curtailment of the positive reinforcement. So in IS code 456 2000, page number 44, in clause 26.2.3.3, there is a point that we have to understand. At simple supports and at point of inflection, the positive moment tension reinforcement, don't go with the positive value, we are interested with the tension reinforcement, as the middle portion of the footing undergoes tension. So tension reinforcement shall be limited by or limited to a diameter of the bar such that LD computed for FD, that is the 0.87 Fy, should not exceed M1 by V plus L naught. So from IS 456 2000 clause 26.2.3.3c, the diameter of the bar should be limited such that M1 by V plus L naught should not be greater or equal to, or this should be greater than equal to LD, that is development length should be smaller than this value. So for which we have to calculate M1. M1 is nothing but it is the moment of resistance of the section, assuming all reinforcement in the section are stressed to FD, that is the design strength, and for this value we will consider Fy as, or FD is 0.87 Fy. This is basically FD is equal to Fy by 1.15. if we divide this value we will get 0.87 Fy. Now this is the value for M1, that is 0.87 Fy AST into D minus 0.42 XU. Now where XU is 0.87 Fy AST by 0.36 FCK into B. We can get this in Annex G of IS 456. Now substitute the value of Fy AST 0. and FCK and B. AST will be provided as 2010, which we have provided for the longitudinal reinforcement at top. So we get 80.95 mm. This is the depth of neutral axis, and similarly substitute the value here, 0.87 into 500 into, so 10 into pi into 16 square by 4, so this comes as 2010 into D is 492 minus 0.42 into 80.95, so which we have already computed here. Now take this value, this comes as 40045317.4 Newton mm. So I am converting this into Newton mm. Similarly V, we have already computed the shear force at the point of inflection, that is the point of contraflexure where moment changes its sign. We have computed the value of shear force at both contraflexure, and taking the maximum value we get 260.7 kilonewton, and in converting this into Newton, 260.700 Newton. Similarly development length, this is also from code, you can find LD is equal to 5 sigma s by 4 into tau BD, and this is sigma is the bar, phi is the bar size, sigma s is the design stress, and tau is the bond stress. And 16 into 0.87 into 500, sigma s design stress, so 0.87 500, 4 into 1.2 for M20 concrete into 1.6, that is increased by 60% for deformed bars, so this comes as 906.25 mm. Similarly, L naught is the anchorage length and it should be taken greater of the two value, that is 12 phi or D. Phi is the bar size, 12 into 5 we have taken 16 mm, so 12 into 16 comes smaller than that of the value of D, so we are taking D, and L naught is equal to 492 mm. Now substitute the value and we'll get 2028.06, which is greater than, this is 906.25 mm, which is okay. Hence the bar size provided, that is 16 mm, is okay for the tension reinforcement for the footing. So we are done with the longitudinal reinforcement. Now we have to provide reinforcement in the transverse direction, and in transverse direction the footing is designed as a cantilever beam supported at the face of the column, and reinforcement is provided considering transverse beam of width is equal to width of column plus 2 into dy. Effective depth in transverse direction. So we will do as per the isolated footing, that we considered a footing or a beam of the width equal to the projection on either side of the footing. So we have to design for both the column, that is column A and column B, and the reinforcement is provided as per the moment computed at the sections. So for column A, the width of the transverse beam, so as I have said, the width of the transverse beam is taken as the width of the column plus 2 times of the depth if available. We have to understand this point. So the value computed for D was, also we have to understand that we are taking the depth along transverse direction, so the depth along transverse direction will be different. So if we see the section in this way, then we will get the footing section in this pattern considering this section, and we have longitudinal rebar along longitudinal direction, that is the along x direction. So this will be the rebar, that is the longitudinal rebar, and the transverse rebar will be at the top of the longitudinal reinforcement. Now for this, the effective depth will be D minus clear cover minus the longitudinal rebar minus D by 2, because we are in the transverse rebar is provided in this manner and it is above the longitudinal rebar. Hence the effective depth is 550 minus 50 longitudinal rebar 16 minus, assuming we will provide transverse reinforcement of 12 mm, 12 divided by 2, 476 mm. This is the depth along transverse direction, and the width of the beam is taken as width of column plus 2 into dy. But for column A, the projection from the face of the column at the towards the left edge is restricted to 0.42 mm. That means this depth is not available, or this distance or length, or we can say width, is not available, so we'll take 0.42 only. So 0.42 plus width of column, that is 0.3 plus d, which is 0.476. I hope you got this point. So the width of the transverse beam b dash is equal to 1.2 meter, and similarly length of projection, so the projection is this, so it will be equal to bf minus dA divided by 2, or we can say bf divided by 2, so we'll come this at this point, minus depth of column A divided by 2, we'll get this much. So this comes as 0.6 meter. Factored load for the transverse beam, so we'll convert the point load acting from column A into a UDL. So factored load, so 1.5 into PA, which is 300 divided by BF and the width of the footing, so we'll convert the point load acting as a UDL along this width. So 300 kilonewton meter per meter, we get this value because BF is 1.5. Considering cantilever beam with UDL, that is from the face of the column, considering this much projection as a cantilever beam subjected to a UDL, then it will be WL square by 2. The UDL is 300 kilonewton per meter into the length of projection is 0.6 square divided by 2. So this comes as 54 kilonewton meter. This is the bending moment acting along the projection. Now area of steel for this bending moment is computed using this formula. Substitute the value of M as 54. The value of B dash will be the width of the transverse beam, that is 1.2 meter. D is 476 mm, and other things will remain same. So B dash 1.2, that will be 1200 mm. Similarly this will be 476 mm. We get 266 mm square. Don't get confused, we are not using 1000 mm, that is we are not considering unit width. So 266 mm square. Minimum area of steel of the section. So as I have already said, so we can use 0.12% if we are using high yield strength deformed bars. So 0.12% of B dash D. So substitute the value of B dash and D. D will be 550, B dash will be 1.2, that will be 1200 mm. So finally we get 838 mm square. So this is the reinforcement required for the transverse direction under column A. So as we have already said, we are using phi as 12 mm. Then we have spacing required as width of the section divided by area of steel required divided by area of the rebar. So the spacing required 1200 mm. So 1200 mm divided by 838 divided by 5 into 12 square by 2, that is considering the minimum area of steel required, and this comes as 161.98 mm. As I have already said, we will provide spacing of minimum 150 mm, so provide spacing at 150 mm. So number of rebars required will be 1 plus, because it will give the number of spacers, 1200 divided by 150. So this comes as 9 NOS. So 9 number of rebars is required. Similarly for transverse reinforcement under column B. So if we see this is the column B, then the number of transverse reinforcement required. For column B, it won't be a problem to get the width of the transverse beam because the length is available at the either side. So the projection is 0.93 meter from the center of the column, and if we subtract 0.2, so it will be 0.73 meter, and the width of the transverse beam from the face of the column is 0, that is the value of D, which is 0.476 on either side of the face of the column, and this will be 0.4. So this is the width of the transverse beam. So width of beam is 0.4 into dy into 2, so this comes as 1.35 meter. Length of projection, so it will be same, 1.5 by 2 minus 0.4 by 2. Sorry, it won't be same because the width of the depth of the column is different. 0.4, it was 0.3 previously, so it comes as 0.55 meter. Factored load 1.5 into 450 divided by 1.5. 450 is the load from the column column B, and it is distributed along the width. So 1.5 is the factored value, and 1.5 is the BF, that is the width of the footing. So this comes as 476 kilonewton per meter. And for the bending moment, again we'll consider a cantilever beam subjected to an UDL with the span 0.55 meter, and the value of UDL is 476 kilonewton meter. Now WL square by 2, so this comes as 60.5 kilonewton meter. So this is the bending moment in this projection, that is this. Okay, area of steel required for this bending moment. Substitute the value of M as 60.5, B dash will be 1.35, that is 1350 mm, dy will be 476. Substitute the value and we'll get 296 mm square. So this value is smaller, so we have to compare with the minimum area of steel. So the minimum area of steel will be 0.12% of BD, so it will come as 900 90 mm square, considering B dash as 1350. Okay, assuming phi as 12 mm, so spacing required will be width of the section divided by area of steel required divided by area of individual rebar. So this comes as 154 mm, and providing 150 mm, the number of rebars required will be 1 plus width of the section 1350 divided by spacing provided 150 mm. This comes as 10 NOS. Provide 10 numbers of 12 mm bar at 150 mm center to center spacing as a transverse reinforcement under column B. Previously we provided 9 numbers of 12 mm bar for the section under column A. Similarly, if we see, we have provided reinforcement in longitudinal direction as well as transverse reinforcement for the critical section, but for section where the main reinforcement is not provided, we have to provide nominal reinforcement, which is the distribution reinforcement, we can say as a temperature reinforcement. So we'll provide 0.12% of the cross sectional area as the distribution reinforcement. Distribution reinforcement is equal to 0.12% of BD considering unit width. So 0.12% into 1000 considering unit width into 550 depth, which we have provided. This comes as 660 mm square per meter. Don't get confused with the value meter, because as we are providing unit width. Providing phi as 12 mm, then the spacing required will be 1000 unit width. So 1000 divided by 660 area of steel required divided by area of individual rebar, 171 mm. Provide 12 mm bar at 150 mm center to center where main reinforcement is not provided. So now let us see the reinforcement details. So this is the footing details, that is footing size is 4 meter length, and converting this into feet we will get 13.1 feet. So I am just showing you how to represent in the real field. And breadth is 1.5 meter, which comes as 4.92 feet. Similarly, depth is D 0.55 meter, 1.8 feet, and depth of footing from ground level, as we have assumed this as 1.52 meter, that is 5 feet. Reinforcement details. Now I have represented the reinforcement details in terms of number, bar size and spacing. At top, so we have provided reinforcement at top and at bottom separately, and for top the longitudinal rebar was 10 number of 16 mm at 150 mm center to center spacing. Similarly, transverse rebar, we can say distribution rebar, as we have not provided separately, so we will take the distribution reinforcement phi 12 mm at 150 mm center to center spacing. Similarly, at bottom we have longitudinal rebar as 10 NOS, as we have provided same for top and bottom, 16 mm 150 mm center to center spacing. Transverse rebar under column A, 9 numbers of 12 mm at 150 mm center to center spacing. Under column B, 10 numbers at for 12 mm at 150 mm center to center spacing, and where there was no reinforcement or main reinforcement, we provided 12 mm at 150 mm center to center spacing. Now let us see in the figure. So this is the reinforcement detailing. First let us see the sectional view. So here you can see this is the green line here at bottom is the longitudinal reinforcement for the bottom, that is 16 mm at 150 mm center to center spacing, and if we see in the bottom plan, this green line represent it as 16 mm at 150 mm center to center spacing, which is provided along the transverse direction, that is along the width of the footing. Similarly, these red circles represents the transverse reinforcement under columns. So 12 mm at 150 mm center to center spacing under column A up to width of 1.25 meter, that was the width of the transverse beam. So 0.42 plus 0.3, that is the width of the column A, plus 0.492. so up to this point we have provided transverse reinforcement of phi 12 mm at 150 mm center to center. Similarly, for column B it was 0.492 plus 0.4 plus 0.492 as 1.35. So we have provided up to this the transverse reinforcement, that is 512 mm at 150 mm center to center spacing. And in other section except the transverse reinforcement, we have provided the distribution nominal reinforcement, that is 512 mm at 150 mm center to center spacing. So this black line represents the nominal reinforcement for the bottom plan. Similarly, at the top we have 516 mm. The green line represents the main reinforcement, that is the longitudinal reinforcement, 516 mm at 150 mm center to center spacing. Similarly, for top reinforcement we provided nominal reinforcement as a distribution reinforcement, so 512 mm at 150 mm center to center spacing. And if we see in this view also, we can understand, so this black line represents the nominal reinforcement, which is 512 at 150 mm center to center spacing, and the green line represents the green circles represents the main longitudinal reinforcement, which is 516 mm at 150 mm center to center spacing. So for check of development length, so we have computed LD as 5 sigma s by 4 into tau bd, which we computed 902 mm, and the available length here you can see this is 0.55 meter considering this section from column B. The projection was 0.55 meter and the depth is 476 mm. Okay, so available length is nothing but 0.55 plus 0.476, so we get this value as 1020 mm. Okay, converting this into, so available required development length was 902 and the available length is 1020 mm, so it is okay. So the next step is check for one-way shear. So if we are computing the bending moment, or if we are computing the depths considering the bending moment, then we have to check for one-way shear. So I am just showing how to check for one-way shear, and it has to be done for the column with the higher load, but for now I am showing you for the both columns so you can understand the point. For column A, the critical section is at distance D. So this is a common point we know from the isolated footing as well, that is the critical section for one-way shear lies at a distance D from the face of the column. But for now, the value of or the shear force has to be computed on one side of the face of the column, that is whichever is the critical one. So if we see the shear force diagram, the shear force at just left of A is 150 kilonewton and the shear force at just right of the column A is 300 kilonewton. So that means we have to check for the greater value. So we'll check the shear force at a distance D from the face of the column, that is from the inner face of the column A towards the right. So for the critical section, the shear force is 300 minus 0.3 divided by 2 plus 0.492 into 262.69. So what is this value? This is the maximum shear force that is at the center of the column A minus this is the UDL 262.69 into critical section is 0.492, that is D from the face of the column, plus mid distance of the column, that is this value is computed at the center of column A. If you see the shear force diagram, this is computed at the mid or the center point of the column A. Hence we have to compute the shear force at the critical section considering the UDL from the midpoint of the column A. Hence 0.3 divided by 2 plus D into UDL. So 300 is the shear force minus computing the UDL up to the span from the center of the column A to the critical section, that is D. So 300 minus 0.3 divided by 2 plus 0.492. So this value comes as 132 kilonewton. Similarly, If we follow the sign convention, then it will be minus 132. You can use the similar triangle rule as well. So if you compute at a distance d plus 0.490, you can get the value of shear force at the critical section. Now nominal shear stress tau v is equal to vu by b into d. So we'll take the magnitude only, we don't compute with respect to sign. So 132 into 1000 divided by 1500 into 492. So this comes as 0.18 Newton per mm square. So as I already said, you can compute with respect to the similar triangle rule as well. So let me show you. 300 divided by 1.14 is equal to, the critical section lies at a distance d plus 0.3 divided by 2. So we are considering at a distance 0.3 by 2 plus 0.492 as x, then 1.14 minus. So we are computing at this point particularly. If we see, then this distance will be the 0.3 by 2 plus 0.492. Okay, this much is 0.3 plus 0.492. 1.14 minus we have to do, so we'll get 132 kilonewton. And substitute the value 132 into 1000 by 1500 into 492, we get this as 0.18 Newton per mm square. Similarly, providing P% as 0.27% and M20 concrete, P% is equal to 2010 1500 into 492, so we get 0.27%. Okay, provide, and M20 shear strength of the concrete is equal to nothing but, this is from SP16, so 0.85 into under root 0.8 FCK under root 1 plus 5 beta minus 1 divided by 6 beta, where beta is nothing but 0.8 FCK, 6.89 into P percentage. So we can substitute the value of FCK and P%, we'll get 8.6, and this value should be greater than 1. Now substitute the value in tau C, so this is tau C, 0.85 into under root 0.8 into 20 into 1 plus 5 into 8.6 minus 1. This square root is different. Okay, it is the minus 1 value is out of the square root, so this comes as 0.3 Newton per mm square. Since the nominal stress, which is 0.18, and shear strength 0.37, so tau C is greater than tau V, it is safe for one-way shear. For one-way shear check under column B, we have to follow the same process, that is the critical section is at distance 0.492 from the face of the column, or we can say 492 mm from the face of the column. Then the shear force at the critical section, either you can use this concept, that is the shear force at the center of column A, column B, and considering the UDL up to the critical section, or you can simply use the similar triangle rule here also. So if we consider point B, the maximum shear is 357, then we have to check for the shear force towards the inner face of the column B. So let me compute the, so suppose the critical section is at distance D plus, so the face of the column, okay, don't get confused, so the shear force at a distance D, and this will include D plus half of the column width, so 357, and this length is 2.5 minus 1.14, so 2.5 minus 1.14, this is 1.36, is equal to, considering this as x, 1.36 minus this, so which is 0.492 plus 0.4 by 2. The width of the column B is 0.4. So the value is 175. Okay, 175.35. So shear force at critical section is 175.3 kilonewton. Similarly, nominal shear stress will be Vu by B into D. substitute the value of B as 1500 and this as 492, we get this value as 0.24 Newton per mm square. Now for P percent as 0.27, which will remain same for column A and column B, and M20 concrete, shear strength of the concrete will be tau C is equal to 0.37 Newton per mm square. Since tau C is greater than tau V, so it is safe against one-way shear. So I hope you have clear the concept that we have to check for one-way shear only for the load with the higher value of shear. So the maximum value of shear was 356, which was for the column B. So if we check for column B, then it will be automatically safe for column A as well. The same concept will be used for two-way shear check, that is, we'll check for the column with the higher load. So similarly for two-way shear check, the check has to be done for the column with the greater load, and the critical section for two-way shear is at distance d by 2 from all faces of the column, that is, we will check for the tributary area 0.246 mm. Similarly in this direction as well and in this also. So this will be the tributary area for two-way shear check. The length of the tributary area is 0.246 plus 0.4 plus 0.246. So this is 0.892 and this will also be 0.892. And the perimeter of the critical section, as I have already shown the tributary area, so the perimeter is nothing but 2 into L plus B. So substituting the value as 0.892 or we can say 892 mm, so we get B naught, this is the perimeter, we get this as 3570 mm. And the area of resisting section, so it will be B naught into D, that is the area which is responsible to withstand the punching effect of the column or a punching effect of the load. Punching shear force Vmax is equal to 600 minus 173.1 into the a plan area of the critical section. So for calculating the punching shear force, the factored load coming from the column B is 450 into 1.5, which is nothing but 600 kilonewton. Okay, 600 minus 173. So if you remember, the net upward swell pressure is 175.1 kilonewton per meter square. This was per unit width, but for now as we are considering an area value, so we have to use this value, that is 175.1 kilonewton per meter square. Okay, so 175.1 into the plan area of the critical section, this area, so which is 0.892 into 0.892. So 600 minus 175.1 into 0.79 and we get this value as 462 kilonewton. Basically two-way shear effect, or you can say this is the punching effect, and this is due to the action of the column load and the swell pressure. If we see the punching effect, so if this is the critical area, the punching effect is that this area tends to go inside. Okay, it tries to punch it down. So the punching shear force is 462 kilonewton, and the nominal shear stress, again Vu by the area of resisting section, and this is 462 into 10 to the power 3. Previously, as I said, we will do two-way shear check for an area, but for one-way shear we did along the width. We substitute the value as B into D, where B was the width of the footing. So the width of the footing was responsible for one-way shear, but for two-way shear, a perimeter, the critical, or we can say the tributary area, is responsible for resisting the two-way shear. So for now 3.57, converting this into, or we can say, right, 3570, let us 3570 into 492, so this comes at 0.26 Newton per mm square. And for permissible shear stress, from IS code we have tau C max is equal to Ks into tau C. From page 58 of IS 456, clause 31.6.3, if there is no shear reinforcement, we have to make sure that the shear stress at the critical section shall not exceed Ks into tau C, where Ks is 0.5 plus beta C but not greater than 1, beta C being the ratio of short side to long side, and tau C is 0.25 under root FCK in limit state method of design. So Ks is equal to 0.5 divided plus beta, ratio of shorter side to longer side. So this comes as 1.5 and this value should not be greater than 1. So taking Ks as 1 and tau C 0.25 under root FCK. So this comes as 1.12 Newton per mm square. Since tau C max is greater than tau V, that is the permissible shear stress is greater than that of the nominal shear stress or shear stress at the critical section. So it is safe for two-way shear. So in this way we completed our video. So we have done the design of the combined footing considering proportioning of the length, net upward swell pressure, bending moment, shear force, longitudinal reinforcement, transverse reinforcement, check for one-way shear, two-way shear. Similarly we did check for development length. So this should be sufficient for the design of the combined footing. I hope it helped you, and if it did, do like and subscribe. Thank you.